Welcome back. Please take a moment to make sure that you are reviewing the entirety of the PowerPoints that I post. I will not have time, unfortunately, to provide you with an accompanied video for every slide. As it is, I'm doing my best to provide you with more than what I think most students are typically provided in terms of online courses. So I do want to take some time to discuss a couple of important ideas. Let's start out by talking about variables. We've discussed before, you've seen in both the book and in the PowerPoints, that a hypothesis is a relationship between two variables, an independent variable, or x, and a dependent variable, or y. The independent variable is the variable that is designed to predict the value of the dependent variable. Also, you should be aware that you could have more than two variables in the hypothesis. You can have another kind of variable that's called a mediating variable. This variable then is kind of in between the independent variable and the dependent variable. So, for example, if I think that increased family time will improve student performance, and I have a mediating variable that says, well, increased family time should improve the student's confidence, which then, therefore, improves student performance, or something like that. So then I'm saying that x impacts y through x2, if you will, if we call the mediating variable x2. We could also have a moderating variable that says, for instance, that as x increases, y increases, but if the moderating variable, which is in the middle, increases, then the impact of x on y will decrease or increase even more. So, for example, the relationship between inequality and health outcomes can be moderated by the amount of or the degree to which healthcare is made free and available to all. So you can have a society with higher inequality, but if healthcare is made free to all, that may buffer the impact of the inequality on health. Or if the society is highly commodified and the healthcare is highly commodified, as it is in our own society, and everybody has to purchase healthcare, then the higher inequality would be enhanced. Its impact on healthcare would be enhanced because only those who are wealthy would be able to afford good healthcare and so forth. Now I've said that, I want to talk about what you see on your screen. Correlation is not causation. Here, you might have heard that before, but oftentimes the tendency is to think, okay, if two things correlate, they cause each other. But I'm going to show you that that is not the case. First off, a relationship means that something is held in common with the variables, and we've talked about those. You can have a positive relationship, which is as x increases, y increases. You could have an inverse relationship, as x increases, y decreases, or you could have a null relationship. Nothing happens, right? That's what we would see in terms of a correlation. The two variables tend to move with one another in either a positive or an inverse way. So these values will be written as in the forms of a -1 or a +1. A -1 is a perfect inverse correlation, and it's as strong a value as you can get. You cannot go higher than -1. I know -1 does not sound high because it is low, but it is in terms of the strength of the correlation, it is a perfect negative correlation, or a +1. Again, the opposite extreme. No relationship or no relationship is reflected as a 0. But what can happen is we can have a spurious relationship, and that is something that appears to be caused by one thing. There's the appearance of a relationship, but it's really caused by something else, or it's just somehow coincidental. So here we are seeing the spurious correlations. So you can take a look here. You've got suicides by hanging, strangulation, and suffocation that are somehow caused by the U.S. spending on science, space, and technology. That does not make any sense because one does not cause the other. It is a spurious correlation. We can look here. The number of people who drown by falling into a pool somehow correlates with films that Nicolas Cage appeared in. Now, some of us may not enjoy the films of Nicolas Cage, but it is doubtful that those films led us to suicide, and particularly suicide by drowning. Of course, with spuriousness, we oftentimes have another explanation. In this case, Nicolas Cage films come out in the summer, and people are also more likely to go swimming in the summer, and so the number of drownings are also more likely to increase during the summertime. But it's very interesting to see this sort of spuriousness. And just scrolling down here, I want to show you some of the sillier ones, such as this one. The letter in winning words of Scripps National Spelling Bee correlates with the number of people killed by venomous spiders. Now, this is one reason why theory is important to connect to methods. Otherwise, you might be stuck thinking that in some way there is an actual real relationship between these two phenomena. What we see here is that spuriousness refers to when two variables correlate with each other but have no causal relationship. They lack that causal explanation. So oftentimes it's because both the dependent variable and the independent variable are caused by a third variable. Another important thing to keep in mind is that there's a lot of emphasis on something called statistical significance. Now, statistical significance means that a particular relationship between two variables is not likely due to chance, right? And so you can be 99.9% sure that it's not due to chance. And that if you were to take another sample, you would have similar results. That's really what statistical significance refers to. And while that's really an important thing to say or to find out in research, it doesn't say anything about the size of a particular relationship. So the magnitude of the relationship is really important. Again, we're at this closer to 1 or minus 1 in terms of a correlation. And this is, of course, in the standardized form. When you do regressions, which is an advanced statistical technique, you then can look and see non-standardized numbers. Okay, you may not have 1 and minus 1, but you should be aware that it's the size of that relationship. How much does a unit increase in X lead to an increase in Y? How big is that increase in Y for each unit increase in X? That's the idea of magnitude. And that's really a fundamental concept that tends to go along with statistical significance, because usually the bigger the increase in Y due to an increase in X, generally the greater the statistical significance. However, if you have a very large standard error, you can not have statistical significance in that event. So, for instance, there's another concept here to be concerned about, and that is if you have something that approaches a perfect correlation, it might not be necessarily a good thing because it could be measuring the same thing. For example, infant mortality is basically perfectly correlated with under 5 mortality, so using one or the other becomes important. If you're interested in using this as either a dependent variable or an independent variable, you wouldn't necessarily need to use both, particularly as in terms of an independent variable. So that's important. You can have the closer two things are to each other, the more mathematically similar they are, and that can reflect that you're measuring a concept that is really similar and not necessarily distinct. And so if you want to include more than one variable or more than one independent variable in your model, then the concept should be different. So here what you see is an example of a correlation table. This is coming from my dissertation. This is a piece out of my dissertation. And you can just take a look and see how the correlations appear. So the one is called the identity matrix. The identity is going down the diagonal, which says that things are perfectly correlated with themselves. And then you can see here that the government share of total health expenditure is positively correlated with physician density, inversely correlated with infant mortality rates, that the more physicians there are per 1,000 people, the less children there are who die before their first birthday. And you can see that there's not really any relationship at all between total health expenditure and infant mortality. Just gives you an example of a correlation table. Finally, I'd like to end with a couple of considerations about hypotheses. There should not be any ambiguity about what you're measuring. In every hypothesis, you should state what are the expected directions. In other words, do you expect it to be positively correlated or inversely correlated? Do you expect them to be moderated or mediated by other variables? The conditions under which that relationships will be held, and unit of analysis should be clear. And that means you need to clearly think through at what level of analysis the variables that you have selected for this are going to be measured. And the confines of the test should be very specific. Remember that in science, everything is falsifiable. So it's important to think that if you're thinking of a research project or something down the road, which you don't have to do for this class, that you can test them with the methods that are available. You should always be thinking about feasibility when you're formulating your hypotheses, as well as the theoretical considerations. Is this going to inform theory? Why do I think this is going to be true? Etc. Anyway, thank you very much.